So my name is Desmond, and thank you very much for attending this seminar here. And I have a chance to share my experience with you all here. I'm very grateful of that. So the topic I would like to share with you today is about advanced miniaturization and power management for wireless devices. Before we begin this agenda, may I have a very quick survey in asking one question. So does anyone here that you may have the experience like me that you find yourself you need to compromise your design in terms of performance or battery life or size to fulfill your customer need, but however, most of the time you just find basically it's a compromise because the limitation imposed by your vendors could be component vendors on the semiconductor size or any other component you need to integrate into your product concept. So how many of you have this experience that that you think you always need to compromise on this? So could you raise your hand? I just see, okay, thank you, quite a lot. So then I hope, until now, that the experience I'm going to share with you is something you can take away after this seminar, and then to move forward, and how to think about another approach that you may not need to compromise in moving forward. TransSiP basically is all begin from a concept called 3D system in package. Oh, sorry. It's really fast forward. Okay. 3D system in package. There was a paper I published together with a central research by at a company called Dai Nippon Printing in Tokyo. They are a pretty large conglomerate in Japan. So at that time, we worked together to come up with a new concept, what we termed as 3D system in package. In 2013 at ICEP seminar in Osaka. That time was possibly the very first time to use this term in the semiconductor history. And since then, the concept of TransSiP was formulated from there. And basically what we do is we focus on what we call transformational system in package and more than more technologies. And these things based on our growing IP portfolio as well. May I move the mic a little bit because I would like to see where I am at. So this is just a very brief timeline of how this thing was evolved. It was at about 2008. I came up with a concept to tell people doing system in package is not something about package. It's something more than that. But at that time, I need to find a partner who are capable to help me to embed component, that means to sandwich semiconductors or any other passive component inside a PCB substrate. Only with that capabilities, then we are able to go something forward. And then in 2010, we came up the world first and possibly the smallest GPS 3D SiP. And what's the breakthrough about that was, it was the very first device as a module that in terms of sensitivities or accuracy is better than the silicon chips that the module is based on. And then in terms of qualities, the CBK is larger than 2, which means the product when go into mass production, the failure is less than 6 in a million pieces. And then move on, we do some other pattern related to 3D system in package and so on and so forth. And 2012, That device was awarded at EDN Hot 100 product in the market, and then move on. So it's all about more than more. I would like to share this picture. I think is, for me at least, the world is pretty worth to looking at it. So for the 50 years, I would say our innovation on mobile technology is following the path of transistor count. It took, from the very first cell phone, 27 years before the very first camera phone came up, and then took another 3 years for the very first video plus GPS phone came up. But however, even today, this is the very famous A10. The silicon count already over 3 billion. So along this wave, I would say most of the innovation that we generated, in this electronic industry, is most likely aligned with the silicon count. That means the processing power, because the booming of the processing power, and then it's bring up a lot of emerging new application, new technology because of this increasing processing power. But however, as you can see the slope of the curve here, gradually slowing down, and eventually now it's flat. So that's why after 50 years, the Moore's law is already end in here. So in this scenario, what's next? Everyone in here as a in the electronic industry, if not the next generation cannot be relied or cannot be driven on the processing power, then where the innovation can come from? In the electronic industry, of course, semiconductor industry, a lot of people are already working on 3D, but it still isn't there. Like the TSV through silicon via has been introduced about 12 years ago. Maybe until this year or next year, there's something more solid to be seen. But today, the 3D IC is the application is still very minimal. Then some major companies like TSMC or Global Foundry, of course, right? They kind of fall back in proposing a 2.5D kind of interposer. But however, the solution is still not the sweet spot, and it's got pretty hot too. You may heard about a story last year. One of the phone people get, if your chip is from a foundry in Korea, not from the Taiwan, one would get very hot. So basically, it's the problem in there. So now, one side, we know we have advancement in process in terms of IC. So we can do a lot of 3D thing on the IC stacking or 3D IC thing. But on the other hand, so many people got the experience, not just digital, but mixed signals, RF, passive component, even PCB layout, or any parasitic, every engineer would deal with every day, parasitic inductance, parasitic capacitance, and this type of thing. Okay, so one side, we have process, and the other side, we have a lot of people with experience. So the industry, the main trend is now, can we merge these two separate things together to become a new roadmap? So the ITRS, International Technology for roadmap of Semiconductors, proposed the more than all is to bring the process not from silicon, from the PCB industry and the OSAT industry, and their substrate technologies can talk about design rule. Today is about here. Progressively move on to like maybe 4 micron meters in the substrate design rule. And from the IC industry, we are no longer talking about the fabrication node. It's talk about, okay, their experience came out from many different applications, MEMS, sensor, whatever. If they can merge, what's next to be happen should be something like 3D SIP. And this 3D SIP is just recently being used pretty frequently in the IC industry to think about how to implement 3D system in package. So that means we need to take a look in the third dimension. We no longer live in the planar technology, but need to think about how to use the third dimension being enabled from our own experience as well as using the available of new process. Here is some example to show you, okay, now we know sort of some kind of component can be inside the PCB. So there are two main process. One we call it is a weir process, and the other is called the pad process. So the main difference between them is the weir process is a sequential process. There could have some active component or passive component be laid inside the substrate and then lay up additional layer sequentially. It's just like how you build PCB today. The advantage of this weir process is conform to the industrial standard today is the laser weir hose, LVH, that the interconnection of the embedded die or embedded passive to be done this way. But the disadvantage of weir process is you need copper plating because all the interconnection is done by laser weir and the plating process. And there are also registration issue. So registration issue means after the component embedded inside, machine vision cannot see where they are. Then how? So that's also introduced another level problem. How you can align the thing and then do the laser weir and interconnection accurately. And also, if you pay some attention here, this layer in between in the embedding layer is called the encapsulating layers. There's no wiring in this layer, so this space become waste. This is one of the disadvantages of this process. And because this is sequential, cycle time is long. So time is money. And the other process is based on path. What this means is a parallel process. First of all, some subassembly were made first. For example, there is a top, middle, or bottom section, and then this component is mounted onto the substrate by reflow process. This interconnection is done by conductive posts. And typically those posts are made by silver plates. And then after this subassembly are made, they lam together in terms of co-lamination subassembly to finish the final layout. So advantage of this is a hybrid process because it will have no limit on using what the most advanced process technology to process these subassembly. Very high density laser or high density PCB can be used as well. And also, these type of component can use from off the shelf that's suitable for the SMT machine that can handle. So the design rule or the registration is not limited by the embedding process, but by the SMT machine in this methodology. But the disadvantage is this is more proprietary. Now, you may have heard about this technology was based on two main categories called Aleph, and the other thing is called B2IT. They also have a disadvantage. The pitch is kind of is quite limiting today. So now we get a kind of pictures that okay, somehow embedded PCB can be done in 3-dimensional. Then how about the logistic? Who responsible for what? Okay, a designer come up with a product concept. In order to do the 3D SiP, that will involve a very specific die that they require wafer redistribution layer. So you will need to have some subcontractor to do that. Circuit layout, and then the wafer into die process. It's also need a very different substrate. Component embedding process, circuitization or SMT back-end process until the 3D SiP is done. In terms of logistic, is also kind of amazing. Assume this is you at here, then you will need your contract, like contractor for processing the wafer from your silicon vendor. So today, your silicon vendor is not supposed to do this. Another supplier on the substrate for embedding process, also EMS for service mount or doing the rest of the work, and then go back to the substrate. Another process for EMS, and then finally is the OSAT for you to do the overmolding, singulation, or that type of thing. So here involve at least different color. Here is 4 or 3 different logistic in this supply chain. In pretty, this actually causing the barrier in the semiconductor roadmap today on how to push this concept forward. So one of the concepts that TransSiP is working on is what we call organic fab. So this term is very similar to everybody familiar with silicon fab. But the major difference is many 3D embedded PCB vendor today, what they are pushing is wiring. So they tell you they have what capability or what design rule that can help you to bring the concept and embed the die inside substrate. But however, what we see the major obstacle that we need to solve is based on what we call IP reuse. There needs to have some circuitry with well-proven IP, functional block, and they are ready to go inside the substrate. So the designer just need to pull out the library and finish their design. And all this is done in an organic fab environment to make it less cumbersome to the product designer. The advantage of that is, in this process, whatever existing IP, they can just draw from the proven IP that they can do for the product design. But if they don't, then work together to come up with new IP which can be reused. And it not just benefits to the original owner, but the IP can be also shared and be reused on another type of product. So in this process also create business innovation as well. So in that scenario, it will become a one-stop shop supply chain that organic fab, this fabrication process would be under one house instead of distributed supplier. Okay, so assume now we have an infrastructure to do that. But what is the key element and help people to innovate? As I said before, we still haven't addressed the issue. We always need to compromise. Then now without the Moore's law, how we can use the concept of more than more and overcome the barrier that the silicon fab cannot deliver. So TransSiP vision is now focusing on 3 things. to begin with. So for the wireless device, we see three essential things that's important. Number one is antenna. All wireless needs an antenna to transmit the signal. And number two is power. Wireless device is always sensitive. And most people today suffer from, or they complain for short battery life. Wireless burn a lot of energy too. Then can we overcome this problem? And the third thing is many wireless devices, of course, need shield. Then can a shield be integrated in the substrate? So first of all, on the top of what people call more than more, we call it more than wire. So 3D SiP is not just about just wiring the thing inside or in 3D to come up with a product. Okay, many people say they can help you to reduce your block size from here to here by 65%. And this has been promoted for almost 10 years, but the successfulness, in terms of measurements, how you measure the successfulness, this model is not that successful. And this is how day back, the very first moment I introduced, day back to 2008, me and the researcher in Japan come up with concept, okay, it's not just about wiring, it's about bring up all the imagination you can think of to deliver something better than the book, better than the silicon vendor can offer to you, or better than any passive component can offer to you. Maybe your capacitor. Everybody know how to use capacitor. Everybody know how to use resistor. But can you do something beyond these type of component? After you acquire the capability to integrate everything in a 3D architectures. Here I would like to give you two examples to begin with. So designer may know in a digital environment that have a processor and possibly this is a very high sensitive or high data rate ADC circuit. If the layout is done by planar technology like this, the traces are really long. That means it's very susceptible to noise or any other interference. But what if the interconnection could be shortened in this way? So designer could very obviously to see, okay, now the inductance be reduced, or the lines are shielded inside the layers. It will bring benefit to the accuracy of the high-speed ADC. Then on another example here is the 3D GPS SiP. We have proven that if the SAW filter can be embedded inside the substrate, what would happen? Is come up, we add parasitic to the SAW filter. The SAW filter is an off-the-shelf component, readily made. It's nothing different than any other SAW filter. But we find we can utilize the parasitic available in this 3D process to come up with new. It's a reborn, actually, it's a re-engineering of this GPS IC, and this SiP perform much better than the original silicon. Okay, so bring this, then we come up three concepts that possibly 3D industry can be used in moving forward. So one is called metamaterial. The fourth dimension is now not just limited to physically 3 dimension. So what metamaterial is? Metamaterial means artificial materials, not exist in nature. Number one, if we want to make the wireless device really small, first of all, is to solve the problem of small antenna. But the problem with small antenna is, for so long, antenna experts, small antenna is designed for portable devices like the cell phone. So cell phone has a reasonably sized ground planes to make a small antenna to be efficiency and high gain. But if today things become wearable, very tiny, the efficiency is no longer there because the available ground plane is so tiny. For example, if the ground plane for GPS patch antenna reduced to about less than 20 millimeter by 20 millimeters, the antenna gains decreased down to 40%. Is already reaching the marginal of a usable GPS antenna. And how about Bluetooth or 2.4 gig? Many people today use chip antenna, but what if the chip antenna is done on a layout just about a US quarter size? Then that chip antenna efficiency goes down to less than 10% or minus 12 dBi gain. So the wireless range is not that really meaningful in that sense. There is a research based on our metamaterials to bring up a new antenna concept, dipole. Everyone knows dipole is the most highest efficient antenna, but dipole cannot be embedded on the ground plane, cannot be embedded on a package. So some researchers came up with a concept like, okay, the blue here is the original dipole without ground plane. But without ground plane is not feasible for multi-layer structures. So if a ground plane is inserted like this, the red line is no longer an antenna anymore. But what if the ground plane is replaced by metamaterial? So now is really a true dipole and the lower frequency range. That means comparatively the size of the dipole is even smaller. So the light blue here is the original, this dipole at a higher frequency. But if you need to bring the frequency to a lower one, that means longer wavelength, right? Longer wavelength, usually the antenna is larger. But now with the metamaterial here, with longer wavelength, but the frequency come down, so relatively speaking, the antenna size is reduced. So this enables a new concept of antenna design moving forward for 3D SIP. So the second thing I mentioned before is power management. All RF designer or wireless people know there's a trade-off between LDO and DC-DC. All wireless SoC or wireless device is so sensitive to power supplies noise. So by default, the industrial standard is to use linear regulator or LDO to give the lowest possible noise that they can get today to maximize the performance of the wireless device. Or they trade off about the performance to power it by a DC-DC, but the DC-DC have a lot of bias noise to interfere the wireless device to degrade the performance. So that trade-off always exists, but until now. And here I would like to show you for DC-DC there are 4 classic noise, what we call the ripple, harmonics, ringing, or spirits. But all this, there's one common thing. All this noise happen in the frequency domain and can be suppressed by some sort of filters to suppress the amplitude. So the common knowledge for everyone is, or we learn from textbook, the more you suppress the noise amplitude, ideally 0, right? Then, noise-free situation, then the performance is supposed to be the maximum. Okay, another thing, IoT wireless device today, none of them is run at peak power. They all run in power saving mode. So like when the transmitter is on, it's only come up a very short burst in microsecond, and then most of the time you stay at the low power state, sleep mode in terms of millisecond or even seconds. Okay, this is pulse nature of the low. This the low current is like this. Then when this low current is like this, traditional designs are powered by LDOs. That means the efficiency is less than 5% because majority of time we stay at the low power stage. That is the fundamental problem why many devices today suffer from very short battery life, because most of the power actually convert into heat in a wireless device. It's not because the 20 nano or 45 nanosilicon consume a lot of current. So if you think that way, it doesn't really make sense. Now, Intel already have a roadmap to 7 nano. Why the battery is still, you need to charge your device every day. What didn't invent is the power conversion node. Now, whatever the best silicon node we have, we still need to waste a lot of energy because today, almost all wireless, the fundamental thing is dominated by no noise environment, and means the power needs to be LDO. So this year, in March, we demonstrated a new technology called SNJ switching noise jitter in Advanced Power Electronic Conference in Long Beach. So there's a new class of noise called switching noise jitter. So today is the very first time to introduce this concept in Hong Kong, and this is being introduced globally with our one of our partners that they do test and measurement equipment. So under this pulse noise nature and the feedback loop at the DC-DC, this noise is not happen in the frequency domain, but is happen in the time domain. Is caused by the timing dislocation of the switching decision loop inside the DC-DC. And we find that if wireless device or wireless SoC need to use DC-DC, even after the amplitude of noise, the other four classic noise, after the amplitude has been suppressed to a certain level, the amplitude of noise is no longer the dominating factor. It will be dominated by the switching noise jitter. But this jitter cannot be filtered by the conventional filter process because this is happening in the time domain and also within the passband. If we can solve this problem, what is going to indicate is even with the power saving mode, the power conversion efficiency would mostly stay at 80 to 95%. Of course, longer battery life. And without the compromise on sensitivities and performance for best spectrum wireless or navigation positioning circuitry. Of course, the benefits is potentially significant increase the battery life and increase the autonomy of the product. And in the end, is user experience. So in this way, TransSiP, based on our finding, we invented a new device called SNJ, Harmony SNJ Conditioner, to replace the original concept of the averaging filter at the output of DC-DC. So with this, we proved this in a GPS device in the field test. This is supposed to be golden standard, powered by the LDO and being tested at the very limiting signal condition. You can see the standard deviation here show the position drift at the lowest minimal signal condition. The position drift is here. But the same system, same setup, same antenna, but only the change is the power to what we call JCPFM. The standard deviation of the position drift is so small. And also the time to first fix, the first time, how quick the receiver can get the position fixed, also improved compared to the golden standard of LDO. So what does it mean? Wireless device today, possibly in commercial terms, the most sensitive device on earth is GPS receiver. If a GPS receiver can use DC-DC with this technology without problem, and the performance is equivalent, and if not better than LDO, that means already equivalent, then it will have a fundamental impact to a power supply methodology to the wireless device. And that may be one of the key things that we can drive forward for the 3D SiP architectures. So if anyone interested in that, if you Google this term, JCPFM, DC-DC, or SNJ conditioner, there are some resources available online that you can look at. Okay, the third thing I have mentioned is the shielding. So the problem today is, of course, everybody knows the shield is bulky, so kind of not fit in IoT device anymore. But we still need it. So obviously the solution, we need to make it very small. Then by how? So this is one of the dimensions we put together for a customer request, because they can only use off-the-shelf component. It's not the type of component we talk about, okay, wafer process or thing, grind to very thin, can be utilized in substrate. Anything needs to be off the shelf, then how we do it? So we come up some micro shielding topology and come up to two parts with what we call interposer carrier package. So the firstly, in here is a software-defined radio. So software-defined radio, they need a lot of different shielding compartment. Then the radio itself, firstly built on a carrier board, and this carrier board can be tested separately before they complete the final assembly together with the shield underneath, which is the carrier. So the interposer and the carrier combine to become one TransSiP package, and also waterproof too. And this technology is now already available from a top-ranked supplier in the US. They are already certified for military standard, and also NASA if it needs to go into space. This is the one possibility 3D SiP can also go forward. Okay, now I hope I have given you a very brief concept of why we take a different approach we call more than wire. It's not about interconnection. It's about, firstly, everyone have a product concept. You don't want to compromise in terms of performance. That means should not be limited by the spec or data sheet provided by your silicon vendor or any other component vendor, but to think of a way on how to make a transcendental system in package approach. So that means when we work together, we are able to create a new IP in a different dimension. And this IP will be able to share and then be reused. So any IP has been generated, they will become proven IP in this 3D embedding ecosystem. So once this thing grows and getting more experience in different applications, in different fields, this also become a new innovative business platform. Do we still have time or running out? I hope not. One slide, I would like to give you a real business case that I haven't included, and why if we go this approach, IP-based approach, will help to business. The 3D GPS SiP I mentioned before, in 2012, it got an award from EDM. But in then 2013, another customer used the same device and got Germany Funkschau Award. because they invented another very small antenna for the automotive. And then 2014, another second vendor, they don't make GPS, but they make clock. So two companies work together to bring up new features not available to GPS device before. And then 2014, basically the same device, they got Electronic Design 101, top 101 component, and they ran 23. So it's really been seen that in the IC or electronic industry that one device can be proliferated to different industry and even different years for different things. So that means for IP we use, the concept is very different to what you do today or I do today in the past. Once you decide this, you hardly to move from one IP to another and to create a new thing because it's mostly restricted by the spec from your vendor. But under this model, it's no longer this way. So after this, I hope everyone can, sorry if I run out. I hope you are able to bring this with you after this seminar and move forward.